We are in the last chapter of the year, 9.1, solving right triangles. I'm going to show you how the book sets up a right triangle. All right, it sets it up in a certain way every single time, and you have to know that information ahead of time. So here's how the book sets up our right triangles for us. Whatever your right angle is, across the right angle, the hypotenuse is always going to be C. All right. Then the other two legs are going to be A and B, and it doesn't really matter where you put the A and B. What matters is what goes across from the A and the B. So this angle up here is going to be always alpha, which makes perfect sense because A and alpha start with the same letter, right? A and alpha. So across from side A will always be angle alpha, and using that same logic, across from side B will always be angle beta. Exactly, okay? So they're going to give you, they may say, hey, beta is this and C is that. Figure out the rest. If you don't put them in the right spots, you don't understand where they go, then you get the answer wrong. So that's how our book sets up all triangle problems. So far, so good? Does that make sense? Okay. When you solve a triangle, you need 6 things for your answer. Okay, you need 6 things. You may know what those 6 things are if you take a guess. Mr. Schroeder.
All the sides and all the angles.
That's right, exactly. You need all 3 sides. And you need all 3 angles. And I make this little chart here to give me all 3 sides and all 3 angles, okay? And in this book, what we're going to do, we are going to just decide to round all the sides to 2 decimal places. 2 decimal places. So we're going to round all sides to 2 decimal places. And we're going to round all angles to 1 decimal place. Round to 1 decimal place. So all sides and angles, so just so that we all have the same consistent answers, and your answers look the same in the back, so you feel validated in your work, we're going to round all sides to 2 decimal places, round all angles to 1 decimal place. Okay, you guys following along so far? No big deal? Wow. Yeah? Hello? Yeah. There you guys are. Okay, yes. So we're going to solve a right triangle, and here's a very typical boring example, and then we'll move on to the more interesting things in just a second, okay? So solve this right triangle. We need 6 things, don't we? Well, we need all 3 sides, and we need all 3 angles. All right, so all the sides are going to be A, B, and C. The angles are going to be alpha across from angle A. Beta across from angle B, and then the one across from angle C is always going to be 90 degrees. So we already have that one, okay? So the information given to us says this, that the B is 2 centimeters, so this one is 2 centimeters, okay? Alpha is 40 degrees. So we really only need A, C, and beta. So we only need 3 things left over. That's why I draw the chart, okay? To give me an idea of what exactly I'm looking for and how I'm going to get it. Is everyone okay so far? Okay, so now that we have the information all set up, what we're going to do is we're going to draw a picture the way the book just wants us to do it, and then solve for the things that we need. Okay, so here's a right triangle. I know that the B, I'll call it 2 centimeters on this side. So if that's where the B is, where does the beta have to go? The beta has to go here. Good. So that means that this is the C, this is the A, and what does that make this angle up here? 40 degrees. Okay, so do you see why it's important to know how the book wants you to set up the triangles? Otherwise, you put the 40 in the wrong spot. It'll be across from the 2, and your things will get all messed up. All right? Okay, can we use the Pythagorean theorem? No, we sure can't. Bummer. Can we get beta really quickly, though? What's that? 50. Yeah, how come that's 50? They all have to equal 180, so that's pretty straightforward. So now we only need 2 things. All right, pretty good. So let's go ahead and get A. All right, we're going to use trigonometry to get A. So let's get side A. Okay, how do I set it up? What trig function do I use? Nope, don't have to do that. Which angle do you guys want to do? Doesn't matter, we know both of them. Pick one. 40? Okay, fine. So if this is the angle we're working with, the 40-degree angle we're working with, what side is the A? Opposite, hypotenuse, or adjacent? Opposite. And which side do we know? The 2, right? So which function are we going to use? Tangent, sine, or cosine? Tangent, right? So we're going to say the tangent of 40 degrees has to be A divided by 2. You follow? Okay, so that means that A has to be 2 times the tangent of 40 degrees. And you all have your calculators out. So I'm going to let you figure out what the tangent of 40 degrees times 2 is. If you're asking the calculator for a degree, what mode do you have to be in? No. You have to be in degree mode if you're asking the calculator for a degree. You knew the right answer. Okay, we need 3 or 4 people to verify the right answer, so the sooner the better would be great. We're doing tangent. 2 times tangent 40 degrees. I hear a 1.68. I hear a second on 1.68. Laura verifies 1.68. Okay, so we're going with 1.68. 1.68, and that we're going to round that to 2. So that means we have 1.68 centimeters. Okay, I'm with you. Great, now we only need one more thing. We need the C. Can we use the Pythagorean theorem?
Yeah.
We sure could. Should we, though?
Yeah.
No. We should not. Why?
Because that's just an estimation.
1.68 is an estimation. It also could be wrong. What if we accidentally did that wrong, and this problem was worth, 6 points, 1 point per thing? Then you would get the A side wrong, and then you'd carry that mistake into the C side, and you get that one wrong too. So let's use the given information rather than the information that we generate just to play it safe. Does that make sense? So I want the C. What am I going to do?
You do the cosine of 40.
Okay, we'll do the cosine of 40 degrees is going to be, no, 2 divided by C. Okay? Now, side note. Here we go. This brings me to a side note. Let's say that you had this. Let's say you had 5 equals 2 divided by x. Okay, how do you quickly get that x by itself?
Multiply by it.
No, you could do that, but then what would you do? Divide by what? No, get the x by itself. We'd multiply both sides by x, right? And then we would divide by 5, right? So essentially all we have to do is switch the x and the 5. So if 5 is equal to 2 over x, then x is equal to 2 over 5. You guys with me on that part? We're going to use that trick over and over and over again. So over here, if the cosine of 40 equals 2 over c, then c must be 2 over the cosine of 40. Ah, very cool. Right? So you're allowed to do that. Okay, so calculator people, help me out. What is 2 divided by the cosine of 40? Let's get 3 or 4 people to verify our results to make sure we're doing right. I hear 2.61. I hear another 2.61. Anybody else out there? 2.612. Okay, we have 5 people that verified. 2.61 is correct. And that makes sense because it is the longest side. Okay? So there you go, guys. We've got, going back over here, we have all 3 angles, and we have all 3 sides, and that's what we call solving a right triangle. Put in the bottom basket for me. Okay? Any questions, comments, concerns, judgments, liabilities, jokes, anything about that? No? We all get it? Well, stage 3, we get it? We could teach the class on that one? Yes? Okay, let's go to the fun stuff now. Here's the fun stuff. You guys see the picture right there? Yeah, okay, what's that picture at? Yeah, I love that picture right there. You guys see it? People standing up. There's a guess. What else you got? A mountain? What else? A dead zebra. What else you guys got? An ant. Trees. Good. This is all good stuff. This is a mountainous region. Good. This is all really good stuff. I'm glad you guys are thinking. It's Alex. No, check this out. I'll tell you what this is. This is a picture of a bridge.
Our bridge.
Your bridge. That's right. Healdsburg Memorial Bridge. Okay. And this is. Hey, what's up? Yeah, you guys are hanging out on the Memorial Bridge. Okay. Judging from the picture there in feet, how far would you guesstimate that this bridge is in feet from there to there? How much? 256? We're going to take some guesses here. Anybody else? 300. Okay, thank God. I thought you said 3. Because it was you're taller than 3 feet, and you're not taller than the bridge. Anybody else?
That's about a football field, 300 feet.
300, that's it? As far as that's it? No other guesses? Guesses are free, and they're just guesses. How much? 270. Oh, you guys are being conservative. I like that. Anybody? Anything else? Based off the picture. 450. All right, now we're talking. 450. Can it be longer than 450 feet? No. No. Okay, so this is a mere ceiling. Okay. Anybody think it's less than 256? Yeah. Yeah. Okay. What do you think? 200. Okay, 200. Can it be any the distance being less than 200 feet? Okay, so we think that our reasonable answer is somewhere in between 450 and 200. You guys with me on that part? Okay, so answer. Somewhere in here, right? Okay, we're going to try and figure this out. Now, imagine that you are back in the 1800s. Imagine yourself in the 1800s. If you're 16 years old in the 1800s, are you married already?
Yeah.
Crazy, huh? So, you want to build a bridge, okay? You don't know how long this bridge is. We can't walk on water, so we can't walk across and see on the other side is, right? It's hostile territory. So here's what we do. Your buddy's over here, and your buddy say, hey, dude, take a walk. And your buddy takes a walk. Down the beach, because we can definitely walk down the beach, no problem, okay? And there's a tree over here. See it? It's kind of hard to see, but it's like right here. You see this little tree there? There's a tree there. So this guy's looking, and he sights that tree up, okay? Now, can we all agree that the tree is not going to move? It's not a trick question. The tree is not moving, okay? The tree is staying where it is, okay? You walk back 330 feet. That you can actually measure, okay? You can actually measure that because you're just walking. You have a measuring yardstick. Take you a while. Your buddy's standing here now, and he takes a line of sight measuring from the tree to where he is now. So where's the right angle? Right? No, not necessarily. That's where he originated from. So here's the right angle. Right? We have a giant right triangle, and we know this is 300 feet, and we know that this measure is an angle of 53 degrees. Okay, because we have protractors, so we can just measure it out. Okay, great. Do we have enough information to figure out the length of the bridge, at least from where he's standing?
Well, right now you're assuming that where they are right now is one end of the bridge and the tree's at the other end, correct?
Yeah, the tree's at the other end of the river. Yeah, other end of the bridge. Correct. Okay. Tree over here. Tree.
Right.
Dude,
And
right
where
there.
they are is the beginning of the bridge.
Yeah, well, yeah, we're like essentially saying we're here,
Okay.
right? For all sakes and purposes. Okay, good. So, how do I solve for this, the distance of the bridge? D. What would I do?
Make a chart.
Make a chart?
Make your chart. 3 angles 2 sides.
I don't need to solve the triangle. I just need the distance. I only need one thing here. I don't care about the rest of it. I just want the one thing.
Wouldn't it be cool to have the rest of it?
It would be cool. Yeah, yeah. Cosine of 53? Cosine would be the adjacent over hypotenuse. This one's the hypotenuse here. I don't know that one. I don't care about that one either. Tangent. So the tangent of 53 degrees would be the distance of that bridge divided by 330. So that distance must be 330 times the tangent of 53 degrees. Okay, folks, help me out. How long is your local Memorial Bridge?
You must have known that like 330, like why would you walk 330 feet, yeah?
I'm just walking around, dude.
437.9.
437.9 feet? Yeah? Sound good? Okay, how long is that bridge? Anybody know? I don't know. Let's Wikipedia that thing.
So that's like not what it really is.
I have no idea. Here's a picture of it, though. I did find a picture. Let's go here, and let's go to... Not train, what? Wikipedia. Ooh. That's not what I wanted. Where?
Last one.
Last one. Good. Where?
Right there. Right next to you.
I don't see it.
Right next
Oh, thank you. Thank you. Okay, what did we come up with, guys? 437. The bridge is 438 feet? What? Math works? No, that can't be right. Ha, no way. The entire bridge is 438 feet. Wow, the longer of the two spans 190 feet, while the deck's blah, 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 blah. Wow, guys, nice job. Math works. That's pretty sweet.
You were 1 foot off.
We were 1 foot off. That's amazing.
I'm 0.1.
Oh, we were 0.1 feet. Wow, that's pretty sweet. All right. All right.
People in Norway know how long our bridge is.
I sure do. Yeah. Okay, great. Here we go. Let's talk about the difference between angles of elevation versus the angles of depression. Hey, now you guys know how long your local bridge is. Cool. Go walk across, count, and verify that. Okay. Okay, angle of elevation. Let's talk about this one. The angle of elevation is like, let's say this is you. Hey, what's up? And you are looking at the horizon. This is the horizon, all right? Then if you're looking at a building, say, the angle of elevation up to the building is created by here, this piece right here. That's your angle theta. That's in stark contrast to depression, not a sad angle. Okay? Bad joke. I tell it in every period. Okay? The angle of depression is, let's say you're on a cliff, and there's a rock down here. Then this is the horizon line. Your angle of depression down to the rock is measured from the horizon line down. That's your angle of depression.
So horizon's like eyesight.
Horizon's like looking eyesight level. Yes. Okay, the horizon line. So it can either be going down or it can be going up. When we do word problems and they say the angle of elevation is blah, 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 you're going to be looking at this type of picture. The angle of depression is blah, 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 you're looking at this type of picture. Do you guys see the difference of where the thetas go? Okay, one goes up, one goes down. All right, let's go to Seattle. Woohoo! Space Needle. Who's been there before? 1, 2, 3. Great. Anybody ever been to the top of the store, where the store is? Yeah? You have? That is awesome. Cool.
Have you?
I have not. No, I've never been to Washington State. I'm in D.C. Okay, question for you. There's this flag on top of the Seattle. Oh, there it is right there. I just want to know how tall the flag is.
14 feet.
14 feet. We have some guesses here. 14 feet's like a little bit taller than the ceiling, just so you know.
27 feet.
Ooh, okay, 27 feet. Anybody else? 38 feet. Anybody else? 50. Ooh, man, you guys are going on. Anybody else? 130 feet. That's what I'm talking about. Anybody else? 6 feet. Did you miss the estimation lesson in 3rd grade? Because there's no way. That's 6 feet. Oh, okay, all right. Because you're 6 feet tall. And if there's a store, now let's just think here. If there's a store in there and people have to walk in the store, could that flag be 6 feet tall? Okay. All right. So does anyone want to go any higher? We think that the highest that flag could be is 130 feet. Anybody want to go any lower than 6 feet? Okay, I want to cross. I'm going to veto that. 14? What do you guys think? Is that a reasonable guess? Like people are into the store right now.
Which part of the store?
The part I'm pointing at.
Which part?
Get rid of the 14? Alex says get rid of it. He's growing irritated. Okay, so 27? Does that sound good? Yeah. All right, so we're going 27 to 130. We think the answer's somewhere in there. You guys cool with that part? All right, so here's the deal. Here's the setup. It's a nice picture. Look at that picture. Isn't that sweet? Yeah. Okay, so here's the picture. I'm going to use this one over here. This is you. Check you out. Yeah. You're having a picnic, and you're looking up at this beautiful Space Needle. You got a friend with you because, you know, friends are cool. And you take a measurement, an angle of elevation. Angle of elevation from where you're standing to the top, the very tip top of the flagpole. And you take another angle of elevation to the very bottom of the flagpole, right there. Okay, so there's a little tiny angle that you've created in between. So let me give you a sideways view of what this picture actually looks like, okay? So there's a flag, and it looks like this. Whoosh. And then there's a Space Needle, and it looks like this, and then there's a little part down here, a little part, and then this comes down and goes out. Wow, that's actually a pretty good drawing. Like that, okay? So you are hanging out with your friend over here, all right? You take a line of sight angle to the top. Ooh, let's just make that taller. Okay, and then you take a line of sight angle to the bottom, and you are measured. We're assuming that this building is a right angle to the ground. If it's not, then those engineers are in a lot of trouble. And you're standing 208 feet away. Okay, that's easy to measure. Yes, sir.
Why are we saying 208 feet away?
This is what you happens to be at.
Okay.
Yeah.
So in the last problem, we walked 330.
Uh-huh.
If it was any different number, we would not have been one off from the actual distance.
No, we would have figured it out. Yeah, because the angle would have changed, right? But the length of the bridge is not going to change no matter what you do, right?
Well, I mean, like, why did you pick 57 degrees and 330 feet?
Why did I pick that? Because that's what it was.
You weren't there. Like, it's a picture.
What do you think I did this weekend? Hey, man, I dragged my wife up here. Said, hey, we got to go do some measuring. And then we got on a plane and flew to Washington and we did this. Come on, man, it's fun. All right, so you do two measures of angle of elevation. Your first one, you have a 71-degree angle of elevation. Fair enough. Your second one, you have a 68-degree angle of elevation. Does it make sense that second one's smaller? Yeah, you're not going as high, right? You're not elevating as high. That's good. We want to know just the height of the flagpole. Okay? So, how do we do it? Yes, we're going to subtract, right? So the flagpole, okay, is going to equal the big one, right? So the big H height minus the little height. H1 minus H2. Does that sound good to you? Okay, so the big height is going to look like this. This is 71. This is 208. This is H1. So someone figure out what's H1. Well, I stepped the other one because we're running out of time. 68, 208, H2. Very good. So we say tangent 71 degrees equals H over 208. Help me out. H1 is how much? The actual height of the Space Needle in Seattle would be
604.
604 feet high?
Yeah.
That's crazy. Really? That's amazing. Okay, then what is the height of H2, the second height? So the tangent of 68 degrees has to equal H2 over 208. Therefore, H sub 2 is equal to whatever that is. Tell me how. 208 tan 68. What do you got? 514 feet. And we said that and we said that flagpole is the difference of the two. So we say that's a 90-foot flagpole? Wow. Okay, so does that fit within our reasonable estimations of 27 and 130? Yeah. It sure does. Okay, let's go figure it out. Is that right? That'd be so cool if that was right. Right? Space. Oh. I don't even know where it is. I don't even know I'm looking. Oh, the top one? Oh, Wikipedia. Oh, I did? Oh. Okay, so check it out. How tall is the Space Needle? It is... Where's the tallest point then? Oh, my 605 feet. That's pretty sweet. And the observation deck is 520. So the difference would be 85. So we were close? We were close. Wow, 5 feet off. It's pretty good. So math, amazing. It's awesome. It does work every single time. Okay, that's it. That's all I got for you. You guys like it?